We're going to get into our Scatterplots unit with statistics today, and this is going to kind of give you an overview of everything that you're going to learn in this unit. It's a very short unit. It's very to the point and basic. We will go a little bit more detail about how to create a line of best fit, which we'll talk about shortly. But let's talk about what scatterplots are. So a scatterplot is a graph that has dots on it, and they're not always going to be in a perfect straight line. They could be random. And it's from data that's collected, and it is to show a relationship between data with two, so that's your first fill in, two numerical or numeric variables. So if you'll notice on this particular graph here, we have numbers on our x-axis and we have numbers on our y-axis. And we're comparing. And this particular one shows relationship between the price of a house and the amount of square feet that it has. So as we can see that we kind of, a trend happens here and then it goes up, the more expensive a house is because of the square foot, or the bigger the home is, the more money it costs, which makes sense. So we use scatter plots to help show trends and to kind of predict what will happen if that trend continues in a relationship. Now, this is not always a cause and effect, so don't confuse that. It's not a causation. It could be, but it's not necessarily going to be. And the way we tell about how close something is related is we talk about its association or its correlation, how they correlate. So it's how closely two variables are related, how they correlate. So to demonstrate relationships, we use the different variables. That's why we do scatter plots. And they represent something, and like our square foot and our price in thousands. And we're looking for patterns in our data and looking for that correlation, how tightly things are together or how spread apart, or if it makes a straight line or not a straight line, or all the different things we're going to talk about. And we do all this because we want to make an analysis of our data. We want to know what in the world is this data telling us. So we have to be able to analyze our data. Now, there are different types of associations that you could see and how things correlate. And we're going to make it pretty simple. So this you're going to have a little bit extra notes on, so make sure you're writing everything down onto your hard copy notes. So as you see here, we have some random dots, and they're kind of following in a kind of a pattern, like almost like a little group of people marching up. And we can think about, if we kind of draw a line in between, we can see that they're going in a positive direction. Think of positive slope. So they're going in a positive direction. And that means as an x is increasing, the y is also increasing. And we can think about the other way as well. If x decreases, y decreases. So the variables are both going in the same direction. One goes up, the other one's going up. One goes down, the other one goes down. And we could see this in a situation if maybe auto insurance, maybe the cost of auto insurance as it goes up. And maybe what causes that? Well, maybe you had a lot of auto accidents. So the more auto accidents you had, the higher your auto insurance would cost. The next one here, we can see if we look at these little dots here, and we think about drawing a line kind of in the middle to encompass what is happening there, we can see a negative correlation, a negative association. And this happens when the x is going up, but the y is going down. Or vice versa. The x is going down and the y is going up. So maybe an example you might see of this is as your mileage on your car increases, its value decreases. The more miles you drive a car, the less valuable it is. Somebody doesn't want to spend a lot of money on a car that's got 100,000 miles on it. So that would show a negative correlation. All right, let's look down at our next ones. So we have one here, and you see how the dots are kind of all over the place. There's no way for me to kind of draw a line that kind of encompasses the way it's going. I could try that way, but nothing's working. So when we have just kind of a blob everywhere, this is a no association or no correlation. So we can't use anything to predict what could happen next. These are just random points. And sometimes you might see this with maybe the color of a car, maybe we had the color of a car down here, and the quality of the car. Well, the color of a car being blue does not make the car run better or run bad. Being red doesn't make it run better or run bad. That has nothing related to it. Just like working out wouldn't cause my hair to grow. They have no correlation. So we do talk about the strengths of how things are, and those strengths are talked about how closely packed together or clustered the dots are. So we've got one more here, and notice that they're packed pretty close together, but it's not, if I do a straight line, I have all this big mess down here, so that doesn't really work. Notice if I kind of follow a line with a trend, I got a curve, and that's not straight. Remember, straight lines are linear, and when they're not straight, we call them non-linear. So this is a non-linear association. All right, let's go down to our bottom graph there, and we have a little point that's out here away from everything else. So we kind of got all of our stuff here kind of going in a trend. Now there is a little bit extra down at the bottom, but we kind of see this is kind of going positive. It may give us a little curve, maybe. We could argue that. But this point out here, it's way away from everything else. That is called an outlier. So we want to make sure we know that this is an outlier. That means it's a pretty good distance away. They're usually pretty obvious. There is a mathematical way for you to find out exactly what it is, but we're not going to focus on that this year. So notice the other piece that we had circled down here where things were all kind of clustered together. Think about a group of friends kind of clustered together, and this person out here is an outlier. He wants to kind of be by himself, do his own thing, and you got a group, and then you have a few people kind of straggling away. Well, this group here that's in this circle, this is called a cluster. Pretty self-explanatory there. All right, so let's talk about how we analyze a scatter plot and the data on a scatter plot. So we've got a couple of different situations here, and we're going to talk about what it tells us. What kind of conclusion can we make about the data? And this is the hardest thing for people to do, to be able to kind of put it in their own words. And I'm going to give you kind of a little key in a little bit of how to kind of be able to speak correctly to tell about your conclusion. So our first one, it says the correlation of gestational age and birth weight. So that's how old someone is when they give birth to a child. So we can see at 29 and it goes up to 43. And gestational age. So if you think about how long someone carries a baby, if they have a baby that is 40 weeks is when you're supposed to have a baby. But if you go over 40 weeks, that baby has more chance to gain more weight inside the mom. So it's going to be heavier when it comes out, usually. If a baby is born at 29 weeks here, we notice that it is much lower in weight than a baby that's born at 40 weeks up here. So as the gestational age increased, so as it went up, so X is going up, Y went up as well. We can kind of think about a positive trend there. So Y went up as well. So when one's going up and the other one's going up, we conclude that this is a positive correlation. All right, so this shows us a positive association, and the way we can think about this is the association of the scatterplot is positive. So we can say this scatterplot is, or shows, a positive association. And what it means is the next part, which means, and now we got to talk about the X and Y. So as gestational age, so we're talking about the X, as gestational age increases, so does birth rate. Because most people, when they get around 38, around this interval, 38 to 42 weeks, usually have their babies. Or the doctors put them in the hospital to have their babies. So we can see as X is increasing, Y is increasing. We don't want to just say as X increases, Y is increasing. We want to talk about what X is and what Y is. All right, let's look at the next one. So the next one says study time versus test score. So we have a test score at the bottom, and we have minutes studied. Okay, so one thing that's missing from this one is we don't see any labels on the bottom there. It's kind of hard to know the test score there, but they do have them marked on the little dots there. You can see what their dots are. So at this one here is 15, but we don't know what their score was. There's no really way to figure out what's going on. And if we think about looking at how the dots are, if we try to draw a line to encompass all the dots, there's no way. They're all over the place. So we can think about, if we tried to do it, it kind of goes up straight for a little bit, but then it goes down, and then it kind of goes up, and then it kind of goes down, and oh, it goes crazy. So this is definitely not linear. We know it's not a linear correlation, and so we could think about that. It's nonlinear, but there's no correlation even being shown. This has no association. So this scatter plot shows no correlation or association. And I use those interchangeably. And that means there's no relationship between study time and test score for this data. Okay, which means there is no relationship between study time and test score. Now that's usually not the case, because when we study for a test and we know what's going to be on the test, we will do better the more we study. However, this could have been just some random data from different classes and they picked up, so we don't really know where they're getting the data from. But in this situation, regardless, in this data collection, there was no relationship. All right, let's look at the next one. We got plastic production, and this is a global situation, probably a big company, and it's talking about plastic production and the year. So we got plastic production and our units here, and we've got the years. So we can see 1951, and it goes all the way up to 2007. It actually goes up a little further, we just don't have it labeled. We can see that as the years increased, we went up in production. Now, how close these are really tight. So this is a positive, this scatter plot shows a positive, but it also is not linear. So it's positive non-linear, where the one we had before that was positive was linear. So this is positive non-linear association or correlation, and which means that plastic production is increasing at a non-constant rate. Now remember what constant is. Constant is slope. When we have a constant, we have slope, which we only have when something is linear. It can be negative, positive, 0, or no, but it's going to be a straight line. When we have a non-linear, we can't ever have a constant. So that means it's increasing, it is going up, and that's what gives it that positive, but it's not at a constant rate. All right, let's go to our next section, and this is plotting points with ordered pairs. And this is just a quick review. We're not going to go through every single one of these, but you do need to fill them out. So remember, ordered pairs represented by an X and a Y. In our situation of scatterplots, the X's are our independents, the Y are our dependents. We've discussed that before. We want to label the X-axis and the Y-axis, and we're plotting some points. We've got some points down here. So remember, we do the X first and then Y. So we go over to 2, 1, 2, and then we go up 6, all the way up to 6. And we're going to put a label of A there. You will do that for each one of these, A through D. All right, so now let's talk about the line of best fit. The line of best fit, sometimes points don't always form a straight line. And we know that they're kind of moving in a certain direction, they're moving in a general direction, but they're not perfectly like little soldiers in a row. So for this example here, we have all these little dots here, and they're moving in a general direction, and that general direction is linear. They're moving in a straight line. It doesn't have a big curve or anything. It's moving in a linear direction. So we can use the line of best fit. It's a line that is very close. Doesn't necessarily have to go through every point, and it probably won't. It's very close to most of the data points. And if you'll notice here, we have a point that it started on. And I can't see that they're going through any other point, but we have a point here. So it's 1, 2, 3, 4. 1, 2, 3, 4, 5. Pretty evenly split. 4 on one side, 5 on the other. Pretty evenly split between them. So it kind of splits that data perfectly. Now, notice that half of the data is above the line and half, roughly, is below. So it has to split that data. This can also be called a trend line. It's another thing you can hear it be called, a trend line. Now, these are actually linear because they're perfectly straight lines, and we're going to learn later how to make an equation for a line of best fit based on data. And you know how to make equations in slope-intercept form, so it becomes very easy. So on these particular ones, we're going to draw a line of best fit through the data. So we kind of think, and you don't have to count all the dots. We want to kind of predict and estimate what's going to go. And if you take one point that you kind of think of as a starting point and continue and just kind of see where you think it's going to go and kind of split that data. And mine's a little bit easier because I have a little extra tools here. I can kind of split my data there. And that might be a pretty good line of best fit. That we also know is going in a positive direction. So this is a positive correlation or association. Notice how they're not super clustered together. They're a little bit more spread out. So that's a kind of a weaker relationship. It's not super strong. It's not making a super straight line. They're not packed super close together, but it's a positive correlation. It might be kind of moderately strong. It's not super strong, but it's moderately strong. When we look at these, we can think about if we start at this point, we want to kind of cut the difference. Let me get my little thing here, and maybe it goes, I don't know, maybe about right there. And that could be a line that we could use to help predict what would continue to happen if we added more to this graph. Now this one, because we created a line that is going down like a negative slope, this is a negative correlation. This was a positive correlation. And notice that these are a little bit closely tight packed together down here. We might have a little cluster down there. And this one's out beside, but it's not too far away from the line, so we couldn't really necessarily call that an outlier. Outlier might be one that's way down here. That would definitely be an outlier. So now let's look at our third one here. We have time per visit in seconds and unique visitors. Well, what does that mean? Time visit where and unique where? Well, we can kind of see if we tried to make a line here, we have a whole bunch over here just out of the way, and then we have a big cluster. So that wouldn't really work, that line there. So maybe I try to do, I don't know, let's see. Maybe here? No, I still got too much away, too much away. So this one, we would have a hard time really doing. It's kind of a no correlation, but we could try, since there's a big bunch down here, we could try from maybe here and maybe go there. That might split them about in half. And those are more spread out on the top and a little closer to the bottom. That might be close. So that being spread out like that, really scattered, almost like scattering beads out, shows that the connection, the relationship that these points have are not very strong. It still might be positive, but it's going to be very, very weak. So we'll call it a positive, but we'll say it's very weak because they're so scattered. All right, so now let's look at plotting points with a table. So we're going to plot the points using the data that's in the table, and we've got to make sure we always have a title and we always label our X and Y axis. And when we look here, our X column and Y column, we have look in the table. Now think about what is controlling something else. Height, the height you are doesn't control how old you are, but how old you are controls your height, especially when you're growing up. So our age would be our X-axis, and our height would be our Y-axis. So that's helpful. So now let's go ahead and label our X and Y-axis. I'll make this a little smaller so we can see it. So if we're talking about age and height, maybe a good title would be age versus height of children. All right, so we already know that our X-axis is at the bottom, so we're going to say this is age in years. And then this would be height in inches. Now, we don't have any labels yet for our numbers. We have to have some type of scale. And I look here, I'm going from 2 to 7, and I've counted, I've got 8 spots technically, so I could start here at 0 and do 1, 2, 3, and go by ones. Here I go from 23 to 48. Well, if I go by ones here, I wouldn't have enough. And if I started at like 2, I still wouldn't have enough. If I go by tens, it's going to be really hard to plot. So you can actually do something when you're graphing on a plot, scatter plots. You can start kind of where you want. And I've already kind of looked to see what my range is between these two and split that data. So I'm actually going to start at 22. And I'm going to show you how you have to account for that. So I'm going to do 22, then 24, and so forth. Just enough. Now, because we jumped this big section here, we jumped from 0 to 22, we've got to notate that. So they do that with a little kind of weird crooked thing. It kind of looks like that. It's almost like they took a bite out of it, out of the chart to kind of let you know that there was a jump in space. And you will see those occasionally from time to time. So now we're going to plot our points. So at the age of 2, we had 23. 3, we had 26. 3.5, we had 24. 5, we had 38. And 7, we had 48. So if we draw now a line of best fit, we can think about drawing a line that goes right through as many points we have. Now we only have 5 points here. So remember they all have to go on there, but we want to kind of split them kind of evenly. So if we think about kind of starting maybe right down the middle, we can always adjust this and think about where we have them. So if I have this one here, I've got 2 on one side and 2 on the other, and it's kind of going through the 1 point. So I've got 2 here, 2 here, 2 here, 2 here, and I'm going through 1. So it's pretty evenly split. So when you're predicting the line of best fit, you're drawing one, you're trying to split that data. So you'll get some practice with that as well. All right, so here are just some basic notes for you to review and to have that have the vocabulary on them So how we would actually use this, if you're ever curious of how one event affects another event, like if I study longer, can I get a better grade on my math exam? Or how do statisticians and quality control technicians, people that gather data that you hear all about everywhere, how do they determine relationships or correlations between events? Between, if I study more, will I make a better grade? So they use scatterplots, and often scatterplots will give us a kind of a look into a relationship and to see if it exists or not. That doesn't mean it's going to, like the one we saw a while ago. We don't know where they got that data. It didn't show a correlation. But if we did our own data, I bet we would see one. So some important definitions to remember. What a scatterplot is. It's a graph that relates two groups of data. Remember, two different variables and their numbers. Correlation is the relationship between two groups of data, and that can be very strong when they're really closely packed together. If they're more spread out, more kind of scattered like marbles across the floor, it could be weak. They could still have some type of correlation, but it could be weak. And then we have a trend line, which we call the line of best fit. You will hear that both. And that what is used is a line that is used to help predict what could happen if that trend continued, or if maybe a point wasn't on the graph and we wanted to kind of know, well, I studied 2.5 hours, what roughly would my quiz grade be? So we have to think about those different things when we're talking about scatterplots. Now, I'm not going to worry about this one too much. We don't really talk about this. This just involves one number. You won't see these, but bereavement data is one we do. This is what we are studying, actually, relationship between two sets of numbers. So scatterplots are those things. Amount of time spent studying and test score received. And then here are some examples about different types of positive correlation. And I also have the word causation. Now, this data here is showing a positive correlation. For example, this might be one where the longer I study, the higher my exam grade would be. The next one is a negative correlation, and you see it going in a negative direction. This may be the longer I study, the worse I get on my exam grade, okay, because it's going in a different direction, or the least I study. Then we have a strong correlation where these dots are very, very close together, and they're clustered. That clustering helps us know that they're really strong, kind of like everybody joining together. They're clustered, and it gives us that strong correlation. Same thing can happen if it's going in a negative direction and they're very clustered. It's a strong negative correlation. Where they're more spread out, but they're still moving in a certain trend, that's weak. It's a weak or low correlation, but we still have a trend. It's still rising, it's still positive, but they're not as clustered as much. That same thing can happen with negative correlation. They can be spread out a little bit more and still be going in a negative direction just because they're not clustered. And then we have this crazy, there's no way to figure out what is happening here, don't know what's going on. We have a no correlation, where we can't determine in a line of best fit and put something there. So remember, correlation does not necessarily mean causation. Just because there's a strong correlation between data does not necessarily mean that one set of data is causing the effect of the other. So that means, like, if I study 5 hours, that doesn't mean that I'm going to make 100. Somebody else may study 5 hours and make 100, but that doesn't necessarily mean that I will. Maybe I'm not studying the same way. Maybe I'm studying the wrong material. Maybe I'm really on my phone more than I'm studying. So we can't necessarily use it for causation. Now, here's the little tricks I told you I was going to give you for helping you write conclusions about scatterplots. So we have to remember that a claim, when we claim something that's happening, we have a claim and we have to have evidence. We can't just say something happened and have no evidence. That gives us an awesome conclusion. So evidence is the information the scatterplot shows you. Okay, it's what it gives you. It shows you, that's your evidence. It's like having the bloody footprint. It shows you. The claim is the conclusion that you can make about the relationship based on the evidence. So for an example, the association of this scatterplot is negative. We can see this line going down, it's negative. That is evident. We can see it, that's the evidence. And now we have to tell what it means. So, which means that a person's age increases, so here's our age, as it's increasing, the time they spend on the internet decreases. So we have our claim without evidence, remember, is just unsupported opinion. Evidence without claim is just unanalyzed information. So we're going to circle the claim. So the claim is that as a person's age increases, the time on the internet decreases. And we're going to underline the evidence. So this association of the scatter plot is negative. That's our evidence. That's what we physically see, and then we made a claim based on that. So some non-examples of making a claim or showing awesome conclusions would be, oh, it's positive because it's going up. Well, obviously, it's not positive, it's not going up. It's definitely not an example. Maybe we say one goes up as the other one goes down. Or one goes up and the other does too. Those are not good conclusions. So here's a template that you can use to help you make your conclusions. So the association of the scatter plot is, tell me what you see. That's what you see on the graph. Is it linear, nonlinear, positive, negative? What are you seeing? Which means that, and then tell me about the relationship using the x and y variables. So tell me about that. Now, you're going to get some practice. Remember that at the end, you are going to be responsible for all of the notes, so make sure you have filled them out fully.